everyone. Welcome back to the class of natural gas engineering. Today we are going to talk about the gas treatment process and let's see what it is and how we can do that. Well, first of all, as you know that we have discussed this chart, that when the gas comes from this wells, the first thing is the inlet receiving. And in the inlet receiving, what we do, we remove any water droplet. We make sure that the pressure is maintained. We make sure the temperature is maintained. So here actually in the inlet maintain, we maintain temperature and pressure. We definitely look for any water, water, remove free water and solids in order to process it. There are water vapors also which can go, but we try to remove as much as possible the free water and solids, and we add corrosion inhibitors so that the plant stays protected from the corrosion because of water vapors because of water. So these are the things that we do in the inlet receiving. Then after we have inlet receiving, we send it through the compression. And the compression job is again to maintain the pressure at the plant. So after the plant, when the compressor increases its pressure and we make sure that the temperature is under control, we go for the sweetening plant. So right now we are discussing this sweetening here, this gas treating. We call it a sweetening plant also at the same time. Okay. What is sweetening? Well, in definition, we can say removal or separation of acid gases. Removal of separation of acid gases from. Now the question is, what are those acid gases? The acid gases are H2S, CO2, and sulfur dioxide, SO2. We have other impurities also, which is carbon monoxide, and all of them, the rest all of them. So mainly we have H2S and CO2 and SO2. These are the main acid gases that we have to remove them because they are H2S is a big problem. A person even can die if we do not consider for H2S. H2S. CO2, it causes the corrosion, reduces the heating value, and so on. So we have so many issues with CO2 and H2S. We don't want them, and they are not helpful and for the for the burning purpose. So we have to remove them. We call them, and remember when the gas has H2S or CO2, we call it a sour gas. So sour gas is called the gas which has amount of H2S and CO2. Okay. Once this sour gas, we we do the process. Okay, we do the process here of sweetening. Then we have three main things now happening here. One thing is this one, we get a sweet gas. Now sweet gas is the one which has no H2S and CO2. No H2S and CO2. Sweet gas. Then the acid gases, for example, you have H2S, we separate them. We have sweet gas goes on, separate them, and other impurities like these, we separate them all. So what we are interested in right now here, we are interested in this sweet gas. So sour gas is the one which has H2S, sweet gas is the one which has no H2S or CO2. This is the base one. Now the question is why we need to remove the acid gases. Well, first of all, as I said, we have to maintain the safe environment because H2S is toxic. If you inhale it, you can become unconscious, and if it becomes too much, you can even a person can even die out of the H2S. So we have to be very careful for the H2S. We have to prevent the pipeline from corrosion. These pipeline plants are very expensive. If because of corrosion they getting pitting or any other issue, then corrosion can destroy the plant. So we don't want any leakage. We don't want any issue with the corrosion pipeline. So we have to remove this one from there. Then we have a prevent maintain the heating value. Some of the gases like CO2 reduces the heating value. So we cannot put it. So we have to remove this heating value. And if the gas is going to the customer which needs which is he will use maybe in further processing, further in any other plant, so these gases has to be removed because they will the reactions will not be stable otherwise. Now, what we need to do when we talk about the sweetening glass, I mean, when we talk about the natural gas purification, we want H2S less than 4 parts per million, and CO2 should be less than 1%. This should be 1. So when we talk about the fuel gas treatment, H2S should be less than 100 ppm. So fuel gas filtering system still work, but in gas it has to be very less than 4 ppm and so on. In ethylene, 1 ppm, and so these are the one. So right now our main objective here is this one, and natural gas purification. So we have to keep less than 4 ppm H2S and so on, and CO2 less than 1. So as I said, H2S is toxic, can take life, and it's flammable at the same time. So we have to remove it. We have to remove the CO2, and there are so many problems we can face because of them. Corrosion at high temperatures, foaming issue, and there are some losses. We use the amine process, and we will talk about it once we discuss the plant. Okay, so what kind of technologies we have to remove this H2S and so we want to remove the H2S and CO2. Okay, we want to remove the H2S and CO2. So what technologies we have? What technology we have? So we have chemical solvents that can do our job. We have chemical solvents. We have physical absorption methods. We have physical chemical blending methods. We have molecular sieve, membrane. So we have so many options. But in order to remove this H2 and CO2 from this amine process. But the most widely used, as you can see from here, are the chemical and physical solvents. These chemical and physical, these two are the most widely used. Mostly the chemical solvents. Here we are going to talk about the chemical solvents a lot here. So very common method. Every plant you will see these one chemical solvents. Okay, here also in Danage they are using this amine process, this chemical solvents one. So now, what kind of chemical solvents are available to remove this H2S and CO2? What kind of solvents are available? So we have monoethanylamine. Okay, we have diethanylamine. We have methyl diethanylamine. We have diglycolamine. We have diisopropanylamine, and we have triethanolamine. Well, most widely, we have too many options for chemical solvents that can remove the H2S and CO2. So, for example, this one, and this one, they are the most common one: MEA, TEA, MTEA. Now, the question comes here: which one to use and why? Well, this depends on the efficiency. How much H2S is there? Okay, how much? Which one is available next to you, easily available for you? How much is the removal of H2S is needed, and how much CO2 is needed? So this depends on the composition and availability and the choice of the one who is designing the plant, so on. So these are the one which are available. Well, amines are the oldest one, MEA, DEA. So right now, this is the most common one, MTEA. This one, methyl diethanolamine. This one is the most common one. They are using to remove the sweetening gas here. So in this lecture, we are actually discuss this amines also. Mostly, we will discuss about the amines. Well, in the most important parameter in the removing of H2S and CO2 is the amine concentration. How much amount amine we are injecting in the system that can absorb the uh, H2S or CO2. So this is the main factor parameter that can remove H2S as per our requirements here in this case. So for example, when we have the monoethanylamine, 20% it can remove H2S and 30% for removing only HCO. So if you inject 20% of H2, the amine, monoethanylamine, it can remove the H2S. And if you inject 32%, it only, so we use, it can remove the CO2 only. Then if you put diethylamide 20 to 25%, it can remove the H2S and CO2. Methyl diethylamine 30 to 55% for removing H2S and CO2. Diglycolamine above 50%. So you can see that monoethanylamine is the most, and diethylamine, they are still the most efficient, and they can be helpful to remove. In fact, they will remove the H2S and CO2 to in a large quantity. These are the structures for uh, amines. Well, they are derived from ammonia, and they have hydrogen atoms with each other, and it has we have primary amines and we have secondary amine. In the primary amine, you can see that it has only one hydrogen atom, only one. Here we have. In the secondary one, we have these are the primary amines here, monoethylamine and monoethylamine formula for amines here. In the secondary one, we have two chains here. Here you can see we have two chains here. These are the secondary amines that we have, and these are tertiary one, which has three, one, two, and three structures connected to it in the amines. So now, which one to use? Like both the amines, monoethanolamine, diethanolamine, and methyl diethanolamine, they have their own advantages and they have their own disadvantages. Okay, they have their own advantages, they have their own disadvantages. This is amine, they are fast reaction, low solvent cost because you need less amount of them, and they are stable also. If less energy cost, less corrosive and highly resistant. But here selectivity means H2S and CO2 both cannot be recovered as we need it. And they have the slow reaction with CO2, it has high solvent cost and minimal COS and CS to remember. And but this one is highly corrosive, this one is less corrosive. So this depends on the composition. If your water like which where what is available and what is the composition, how much CO2 you have, how much H2S you have in the composition, and based on that you remove them. The physical solvents that we use are mostly uh, most famous are the this one water, methanol, and these are the most commonly used uh, physical solvent. And Selexol is also very famous. They use these physical solvents to remove the H2S and CO2 from this gas. Okay, but they have very high capital cost and high solvent cost. I mean, they are not easy to buy. They are not easy to manage them. So they have to replace them. Once they are saturated, we have to replace them. So they have very high cost. That's why we don't use them. We use the amines mostly. And these are by some companies. Shell has their own sulfinol, Union Carbide, Selexol, ExxonMobil, Flexor. So each company they have made their own uh, physical solvents to remove this H2S and CO2 from the system. So these are the reactions, and it has when this H2S reacts with this amine, and definitely it removes the H2S, takes out the H2S with it, and so on. And at low temperature, amine absorbs the acid gas. So temperature also plays very good role in the the process of removing the H2S from the gas. So if you have high amount of CO2, you should not use MDEA because it's not going to remove all of the CO2. It's quite selective in this one. So monoethanol and diethanol amine are the most commonly used, and high favor temperature favor desorption. So these are some of the methods of the one. Now let's look at the some uh, property parameters for. Let's look at some parameters for amines and the physical absorption. We have to compare the amine and physical absorption at what temperature and pressure they can work mainly. So the amines actually monoethanol and diethanol amine. Okay, we are talking about these monoethanol, diethanolamine, methyl diethanol. These are the usual common chemical reactions that they observe, and they remove the CO2 and H2S from there. Well, pressure doesn't matter a lot in this one, but temperature operating matters, and we have through the simulation we have to find the exact temperature at which we get the highest efficiency of it, and we definitely reboil it and we heat it up, and after heating H2S and CO2 comes out of a solution. Temperature is the one which manages this process, well, diethanol and monoethanol amine, these two are okay for H2S and CO2, but if the gas has CO2, MDEA cannot be used because it's used for H2S only. This is the one, and it definitely reads all requirement, but of course the managing cost is high because we have to make it a high temperature, so the the acid gases dissolved from the amines also. Well, again, in this one, the pressure matters in the physical absorption, and it is pressure based mostly, unlike the amine base. Amine mostly using the temperature they do the chemical reaction. Here it is based on the physical reaction and so on. Okay, and now we have two kinds of methods to in amine process. One of them is called as a thermal swing method. Other one is the pressure swing method. In the thermal swing method, it is used when we just change the temperature, and both have limit has issue with the regeneration. I mean, regeneration is the place where the acid gases are removed from the amines, from the rich amines. So thermal swing method use the temperature to dissolve the acid gases, and it is quite efficient in this way. In the pressure swing one, they play very low, but they provide mechanical uh, low pressure required, but mechanical energy more expensive. So it is quite expensive. The pressure swing one, thermal swing one is the most common one that we use here, and the absorption process actually talks about the physical solvents that we use, and they are not quite economical, and high pressure is needed in this case. Adsorption is the one is using by the chemical solvents mostly, and this is quite common use here uh, to remove the H2S and CO2 in this case. This is the basic diagram for a mine process. We have two towers. One of them is called this uh, absorber. Okay, this one is the absorber tower, and this one is the regenerator tower. Well, in the absorber tower, what is happening here? The lean this one lean is entering inside here, and the sour gas is the gas which has H2O, H2S, and CO2, CO and CO2. So this sour gas is going inside. They do the chemical absorption inside, and after the chemical process, the the pure gas C1 to C4 becomes sweet gas and it goes here. And amine, which is now has the acid gases, they go to the regenerator column. Here we give it a high temperature, and using the high temperature they are regenerated. This is the simplest form of the gas treatment process here goes on. So we remove the H2S and CO2 from here, and the rich clean amine goes back from here. It goes back to the one. So rich amine, this is the rich amine. Rich amine is the one which holds the H2S and CO2. Through the heat exchanger, it goes through here, and acid gases are removed there, and this rich lean amine again goes back to here. And the sour gas going here inside from here, and the sweet gas go here, and the acid gases along with the amine become rich amine and goes there. So when these components plus the chemical adsorption happens, we get the sweet gas and some degraded products and so on. What degraded products we get? Well, these are the chemical we get this BTEX, heat, oxycarbon, carbonates, and ammonium and oxalate, and these are the amine base we get from here. The efficiency of the monoethylamine to remove this monoethylamine, the efficiency of the monoethylamine to remove the H2S is quite very good, is 80-100% almost. Then diethylamine is a bit lower, okay, and it's slow. This MEA monoethylamine is very fast reacting, and it has good stability and so on. But this one is hard to use because the H2S we have to remove very uh, high amount of H2S recovery is needed in this case, and then these efficiencies are reducing, and this DG is also good, but mostly we are using this one monoethylamine and diethylamine. But in the MDA cases, it just removes the H2S. CO2 cannot be removed very well from this process. Now this is the typical sweetening process diagram that you will see in the exam also. You have to make this diagram, completely draw it, and I'm going to explain to you this diagram how it works here actually. Well, no, here our equipment number one is this one. This is the inlet separator. What is happening here? We have the sour gas entering inside. Sour gas is the one which has H2S and CO2, and sour gas goes here. This one. This is the tower number two. Okay. Then in the tower number two, H2S is the amines are coming down, and the sour gas is going up. They meet each other. You can say they intimate each other, or they mix with each other. Okay, after that we have this main tower, then we have this main tower, we have this main tower, we have this main tower. So it has basically, uh, you can say, seven basic set of components that are used in the amine process. Now I will prepare the diagram for you. So the first one is the sour gas. Okay, in the sour gas, the gas which has the H2S and CO2 are going into the inlet separator. The purpose of inlet separator, if there is any free water, if there is any contaminant solid, they are removed in this case. Then the sour gas enters inside here and goes in upward direction. But the lean solvent goes in downward direction. They mix with each other. You can say they can kiss each other. So after they mix each other, the sweet gas then goes up and again goes on. And again we put a separator. Maybe there is a solvent and left behind. Some amine concentration goes there. So in the separator we remove it and we send the sweet gas to the gas. Now the rich amine which is now holding the H2S and CO2 goes in this flash tank. In the flash tank, again, we need it because maybe if there's any hydrocarbons, gas particles, we remove them. If there's any liquid hydrocarbon, we remove them. So the gas again goes mixed with this one. If there is any liquid hydrocarbon, we manage it. And now the amine, which is rich, now it goes through in this tower, in the tower number 4. Now this is called the stripper tower. Okay, a stripper tower, or we call it a regenerator tower. Now the regenerator tower, what it does, we boil it. We have a boiler here, you see here, we have the boiler. So we boil it, and using the boiler, we give it high temperature, and because of that, this H2S and CO2 goes out, and we store them in accumulator. And now since this amine H2S and CO2 are removed and goes out in accumulator, the clean and lean amine, it goes back to the system. Okay, so lean amine actually, here it goes back to the system. And then of course we have a set of equipments here. These are the set of equipment just to clean them, filter them. Maybe there is some impurity, some solid, some other. So we, because we want a very clean amine, so they go through all this filtration process and the cooling process, and then the rich amine is sent to here. So this is all the process. So there are seven main components: one absorber, one stripper, flash tanks. If there's any amine, we remove it and we send the gas. Here if there's any gas or liquid, we remove them. Then we have regenerator actually puts on boiler, and H2S and CO2 are accumulated here. Lean amine then sent back to the system after they pass through this one. So these are the seven main amine process components here. So what are the components for this amine process? The major component is knockout drum, absorber, flash tank, exchanger, regenerator, filtration process, and amine regeneration. So we have main seven part, one, two, three, four parts to remove this, and the amine process they are used here mostly. So let's talk about the amines one, the first one. Here is the first one, inlet separator. You see, here's the first one. This is the inlet separator. So before entering this stripper tower, before entering this main absorber tower, the purpose of this inlet gas knockout drum is to remove any free water it has, or if any contaminant it has to be removed. Yes, basically the contaminants that we have in this knockout drum, or we call it the inlet separator. Basically, it removes any liquid hydrocarbons. If it has any water, salt water, it has any sand particles, any component, any other treating chemical or compressor oil. So any kind of impurity or contaminants we call them, they have to be removed. Then the sour gas goes there. Remember, the sour gas is the one which has H2S and CO2. Then we have the amine tower, typical amine tower. And in amine tower, what is happening here? The sour gas is is coming from the downside, and it goes as you see this arrow, it goes, and the sweet this linamine is entering from here, and this linamine is going down. Sour gas is going up. They meet each other. So after they meet, there is a chemical reaction, and the sweet gas goes out, and the rich amine goes from downside and for further processing. So these are the rich amines. So now I will show you a video of the amine tower and bit amine process before we go ahead and to further work on this amine process. Sour gas is entering in the system. Amine is going down. So this sour gas do the reaction with this amine, and sweet gas goes out. The rich amine which is has H2S CO2 goes in the regenerator tower, and that's the process of sweetening mainly. So it's a weak base amine, and H2S and water soluble salt is produced as a final product.
Spartan Energy Partners is an independent single-source oil and gas service company that provides the industry with quality gas treating and processing solutions. We don't take shortcuts, we don't make compromises. We stand behind our services. We call this the Spartan Advantage, a higher standard in gas services. Amine gas treatment is a proven technology that removes hydrogen sulfide, H2S, and carbon dioxide, CO2, from natural gas streams through absorption and chemical reaction. The Spartan Energy team has built a fleet of amine plants with the capability to customize and modify various sizes to accommodate the varied needs of our customers. Spartan designs these units and includes features which improve efficiency, runtime, and operability. Spartan's design philosophy results in quick delivery and quality that exceeds industry standards. Spartan gas. Starting upstream from the gas skid, sour natural gas enters a two-phase separator to remove liquids from the gas. Then it continues to a filter separator to remove particulates. Next, the gas enters the gas skid. Treating continues with the skid-mounted fine filter separator for further removal of particulates. The sour gas then enters the bottom of the amine contactor tower, where it flows upwards, contacting a counterflowing solution of amine and water. This exothermic reaction is induced at high pressure and low temperature through either packing or trays in the tower, enabling the amine solution to remove H2S and CO2 from the gas. The treated or sweet natural gas flows out of the top of the contactor tower to an after scrubber, where any liquid picked up by the gas in the amine contactor drops out. After the gas leaves the gas skid, it then enters a gas cooler. When necessary, a dehydration system using triethylene glycol can be utilized to remove H2O from the saturated gas. The sweet gas now meets the customer's requirements. The amine regeneration skids process the amine output from the gas skids. The rich amine solution loaded with H2S and CO2 exits the bottom of the amine contactor tower at high pressure. Pressure is reduced and the amine enters the flash tank at a low pressure to flash off light hydrocarbons entrained in the amine. The low-pressure rich amine enters the amine regeneration skids. It is then filtered through 3 filters: a rich amine filter for particulates, a charcoal filter for hydrocarbons, and a charcoal after filter for removal of charcoal particulates. The rich amine is then preheated by a plate frame heat exchanger before entering the top of the still column. As the rich amine flows downward, it contacts counterflowing steam at low pressure and high temperature. The steam strips the rich amine solution of the H2S and CO2, leaving lean amine to exit the bottom of the still column and enter the reboiler. Inside the direct-fired reboiler, the lean amine solution is heated. The steam generated in the reboiler enters the bottom of the still column. This steam exits the top of the still column, flows through a reflux condenser, and then enters the reflux accumulator, where acid gas is separated from the water. The acid gas can be sent to a thermal oxidizer or disposed of in other ways. The water is recycled back into the system, being pumped into the rich amine solution by reflux pumps before it enters the still column. Back inside the reboiler, the lean amine flows over the top of a weir and into the surge side of the reboiler, where it exits and is cooled by the same plate frame heat exchanger that heated the rich amine. The lean amine is pumped by booster pumps into a lean amine cooler and into the solution pumps that pressurize it back up to high pressure. The lean amine then enters the top of the amine contactor tower, where the process is repeated. Spartan Energy Partners offers customers comprehensive solutions for treating and conditioning from the wellhead to the pipeline. Our experienced and dedicated team works with your organization to engineer solutions that will maximize gas flow and meet pipeline specifications. Through every step of our partnership, Spartan will assemble the right workforce with the right skills to meet your short and long.
So we close the chapter here. In the next lecture, we will talk about these components, for all the components, as well as we'll talk about the problems that are faced during the amine process. So what kind of problems are expected and how we can solve those problems during the amine processes. So have a good day and enjoy the lecture.